Okay, so thank you, Gianira from University of Zurich, and she will speak about Roos-like bound for skew-cyclic codes in Hemming and some rank metric. Please, Gianira, it's up to you.
Thank you. Thank you for the introduction. And it's a pleasure for me to present my work in Italy this time. So I will present these works that comes from a collection of two projects, actually, which are made in collaboration with Javier Lobillo from University of Granada, Alessandro Neri from Max Planck Institute of Leipzig, and Antonia Wachter-Zeh for Technical University of Munich. So the first part of the talk, I will recall some basic ideas of skew-cyclic codes, and then I will generalize these ideas to skew-cyclic codes in the Hamming metric and in the rank metric, and finally to cyclic skew-cyclic code in some rank metric. So luckily, Elena and Martino before me recap a bit of linear code, so I can directly go to cyclic codes, assuming everything that you heard before. So an NKQ code, which is a vector subspace of FQ to the n, is said to be cyclic if for every code word that you have in the code, then also its cyclic shifts belong to the code. Cyclic codes are very nice because they have a nice algebraic structure, and the aim of this talk is to generalize this algebraic structure also to skew-cyclic codes. Okay. Yeah, so first let me recall what is this algebraic structure in cyclic codes. And so we have to consider this isomorphism of vector spaces. So we consider on the right the polynomial ring FQX, and with the quotient to the ideal x to the n minus 1. And with this map, we associate in the natural way to a vector of length n, a polynomial of degree at most n minus 1. And this is an isomorphism, and so you immediately see that the shift on the left corresponds to the multiplication by x on the right. And so a cyclic code in here, which is a vector space here, has the property that its image under this map is an ideal in this polynomial ring. So essentially, since this is an isomorphism, we identify the code with its image. So I simply say that a cyclic code is an ideal in this polynomial ring. So since this is a principal ideal ring, every ideal is generated by a polynomial. This polynomial is called the generator polynomial. So from the generator polynomial, you can recover all the code word in the cyclic code. So the use of cyclic code can be seen also from here because it's very easy to be stored in the system. You just need to store one polynomial. Okay. The generator polynomial is important because in terms of its zeros, one can give some bounds on the minimum distance. To be more precise, I need to define the defining set of a code. So I take alpha to be a primitive element, a primitive n root of unity. So alpha belongs to an extension field of FQ, so in FQ to the R. And I define the defining set to be the set of indices between 0 and n minus 1, such that alpha raised to the power of these the indices is a root of the generator polynomial of the code. So the idea of using the defining set traces back to 1960 with the BCH bound. And the idea of the BCH bound was then generalized by Hartmann and Tzeng in 1972, and then further generalized by Roos. And I don't want you to focus really on the technical assumption in these bounds, but I will give you just the idea. Essentially, the BCH bounds looks for the biggest subset of the defining set, which is made by consecutive elements. So, and in terms then of these sets, we can give some bound on the minimum distance. The Hartmann-Tzeng looks for a consecutive subset of consecutive elements in the defining set. So somehow is a BCH bound in two directions. And finally, the Roos bound allows to have some gap in one of the two directions of the Hartmann-Tzeng. So this is the general idea of these bounds. There are other bounds on the minimum distance of cyclic codes, but I just will focus on these three. Okay. Now I can go to the skew-cyclic part. So the skew-cyclicity was introduced essentially by Boucher and Ulmer in this collection of papers, and then other authors started to study it. And to define a skew-cyclic code, we needed to consider a field. Also, in the here I did not assume finite, but actually I don't need really to be finite, the field. And then I consider an automorphism of the group, of the field. Now a code in F to the Dn is skew-cyclic if whenever you have a code word in the code, then you also have in the code the shift of this code word and then the application of sigma, that is the automorphism of the field. So you first shift the vector and you apply sigma to each component. And this will still be a code word. So for every code word, you also have this other code word. And okay, and now also skew-cyclic code have a nice algebraic representation. And to introduce this algebraic representation, we need to define the skew polynomial ring. So we still have F, which is the field that we consider, and then we consider an automorphism of the field. And then we define the ring, the skew polynomial ring, as the ring of polynomials whose coefficients are in the field, endowed with the usual addition coefficient twice. But here now the multiplication follows a new rule. It's not commutative, but we have that x times a is equal to sigma a times x. And so we just define this multiplication rule, and then we extend to the polynomial with the distributivity and associativity. Skew polynomial ring were introduced in 1933 by Ore, so it's a very old object, and so relatively recent. It has been used in coding theory applications. Okay. So as we did for cyclic code, we can identify F to the Dn with the skew polynomial ring. So remember that R is simply the skew polynomial ring I introduced before, so F x sigma, and with R times a polynomial, I just denote the left ideal generated by x to the n minus 1. I say left ideal because the skew polynomial ring is non-commutative, but is a left and right Euclidean domain, and so I need to distinguish between left and right ideals. And with this map, we can identify a vector of length n with a polynomial in the same way as before. And so now we get the same correspondence we had before. We have that a skew-cyclic code in F to the n is a left ideal in this polynomial ring. More precisely, its image under this map is a left ideal, but since this is another isomorphism, I can simply identify the object with this image. So nice, we are happy, and just let me notice some property of the skew polynomial ring. Is a left Euclidean domain, as I also write Euclidean domain, and so in particular for every two polynomial there exists an Euclidean division algorithm, and exists a greatest common right divisor and a least common left multiple. And since this is also a principal ideal domain, every code is generated by a polynomial. So every left ideal is generated by a polynomial. So also in this case, every skew-cyclic code has a generator polynomial. Since there is the notion of Euclidean division, and I want somehow to define again the defining set in this context, I need the notion of evaluation. So if you consider a polynomial here, in the skew polynomial ring and the scalar a in F, an element of the field, then we can define the value of F in A to be this quantity here. where this NIA is defined for I greater than 0 by this product, the product of J that goes from 0 up to I minus 1 of sigma J of A. And for I equal to 0, it's simply defined as 1. This is called I truncated norm and is well defined. So we take this as definition of evaluation. So we say that the evaluation of F in A is simply this product, which will be the remainder of the division of F with the X minus A, essentially, with this new Euclidean division algorithm that we can define in the skew polynomial ring. Okay, so thanks to this notion, we can finally define the defining set of code. But first, I need to fix some notation, which is technical, so I hope you can forgive me for this. So I assume that I have two cyclic extensions of two cyclic field extensions, so L over F and F over E. So it's a tower of fields. And I have two automorphisms. One, which is in the generator of the Galois group of F over E, and it has order mu. So E is the fixed field of F under sigma. And then I have theta, which is an extension of sigma, is an automorphism of L, which fixes E. The restriction of theta to F will be exactly sigma. And finally, fix an element in the bigger field in L, such that is a normal. That means that the set alpha, theta alpha, and the other conjugate till theta to the n minus 1 alpha is a basis over E. And last thing, I need to define this beta to be theta of alpha times alpha to the minus 1. This condition essentially means that x minus beta right divides x to the n minus 1, which is the condition that I need to define the defining set, to define the generator polynomial, essentially. And so those are all technical assumptions that lead me to define the defining set. So we take a polynomial G in R, then G right such that G right divides x to the n minus 1, and we consider the code generated by G in the skew polynomial ring. So we just make the ideal generated by this polynomial. And we define the defining set of G, or equivalently the defining set of the code, to be the set of indices such that x minus theta raised to the power I of beta right divides G. So this will be the equivalent definition of the defining set in the skew polynomial case. And what is important is that the least common left multiple of all these linear factors here right divides G. Okay, so we are now ready. Here in the first half of the table, you see again the BCH bound, Hartmann-Tzeng and Roos bound in the classical case. Then motivated by the skew BCH bound that was introduced already by Boucher and Ulmer, and the skew Hartmann-Tzeng bound that was generalized later, we asked ourselves if we could generalize the Roos bound. And the answer is positive, and actually is not very surprising, because essentially we have the same assumption of the classical case, and we can state it in the same way. What is interesting is the proof of this result and the fact that it holds also for the rank metric. So we can endow a skew-cyclic code with the rank metric, which is defined with respect to a field extension F over E. And it is the metric induced by the rank weight, and the rank weight is simply the rank weight of a vector is the span over the base field, the dimension of the span over the base field of the entries of the vector. And so since the rank weight, the rank distance of a code bounds the Hamming distance, actually, one can directly prove the rank weight, but and then you get for free the Hamming the bound for the Hamming distance. But this is not the case, because for the proof of the rank bound, the bound on the rank, you need actually the proof on the Hamming one. So you cannot do this one before the other one. Okay, so just make an example because having a bound like the Roos bound helps to construct codes with prescribed minimum distance. And so this is an example. We do this over finite fields because with the computation are easier. So we take as f, so as middle field, f2 to the 6. As base field, we take f2. And f2 to the 6 is simply given by f2 extended with the a, where a satisfies this rule. And then we take as a sigma the Frobenius automorphism a, which raise a to the power 2. As a bigger field, we take f2 to the 12, which is f2 extended with gamma, where gamma satisfies this other equation. And finally, theta is the extension of sigma, is the Frobenius of order 12. Okay, now we fix alpha, as we did, as in the assumption, we fix alpha to be an element, a normal element in L over F2. So we chose gamma to the 5, and then we have beta, which is suddenly is the same as gamma to the 5 in this case, but it's just theta alpha times alpha minus 1. At this point, when you choose your setting, you can choose the parameters of the Roos bound that you want. So we can choose a b equal to 0, s equal to 1, and the rest. And now you know what can be the defining set. You just plug in to the defining to the Roos bound statement this number here, and using the property that if there is an element in the defining set, there is also its shift by the order of sigma, you get that in the defining set you have exactly these elements here. So now we can compute the least common left multiple of this linear factor to get a polynomial of degree 6, which generates a code which will have a distance at least 4. So the code that you get has actual distance 6. So it doesn't seem too much significant in this case, the Roos bound, because we knew we had constructed code with the distance at least 4. The minimum distance is 6. But what is interesting in here is that you can make the same construction and know the code with the rank metric, and the code that you get is MRD, maximum rank distance, which means that the dimension and the distance and the length are related by this bound. So probably some of you are not familiar with this type of bound. It's still a singleton-like bound. It's not the one that you know probably, but it's the transposed version of that one. Okay, so with respect to the classical bound, it's not MRD, the code. It's MRD only with respect to this one. Okay, so okay, so finally, let me I go fast in here. I can generalize the same setting to the sum rank metric. So assume you have a vector in F2 to the n, which and n is equal L times m, and so you can have that a vector is partitioned in a small block, in a L small block of length m each. You can define the sum rank weight of this vector to be the sum of the rank weight of each small piece. And in this setting, we can define a cyclic skew-cyclic code, which are code closed under the action of these two operators, one that shifts the blocks and one that works inside the blocks by shifting the element of the blocks and apply the automorphism of the field. Cyclic skew-cyclic codes have been introduced recently this year by Humberto Martinez Peñas, and are a nice generalization of skew-cyclic code and cyclic code. And also in here we can define the defining set of those, and I think it's up here because